Okay. So once we find the equation of the total cost, we will derive this expression with respect to diameter to find the optimal diameter that will minimize the cost. Okay. Now, let us consider the analysis that should be performed. Okay. So first, in order to formulate a least annual cost analysis, then the initial cost of an entire system must first be converted to an equivalent annual cost. يعني انتوا already بتعرفوا هاي الكونسبت من ال economical analysis chapter. If you remember نحن وقت نعمل ال NPV method we calculate all value of money at present. صح؟ So we use a certain discount rate in this case. هلا here it's a similar approach. Okay. In this case, what is the situation? We are considering that the capital is borrowed from a loan institution. يعني نحن على بنك واخذنا مصاري, and this is why we will pay this money with time. وفي a certain annual interest rate that must be repaid or amortized with yearly payments. Okay. طيب فإذا من economy we can find we can assess what is the value of the annual cost function of the following parameter: the annual interest rate, يعني قد ايه الفايدة اللي عم بدفعها أنا, the number of years to repay the loan, على كم سنة مقسم الدفعات, والamortization rate. Okay. So this will allow me to find the cost, the annual cost per year that will be paid. Okay. Now, what about other costs? So this is the if you want the cost for the to be able to set the system. تقدر جيب السيستم, أخذت لون, حطيت السيستم, and now what I want to do is to find other costs that I have. So I have first the piping cost per unit length. Okay, the piping cost per unit length is in dollar per meter of piping system, and is calculated as C1 times D to the power n. Okay, well C1 هي constant, هي cost of a reference pipe size بتكون given لإلكم. So C1 is given. Okay, and I can, depending on the diameter of my pipe system, I can assess what is the initial cost per meter. And of course, as D will increase, the cost per unit length CP will increase. Okay. Now, N is a dimensionless exponent in pipe cost equation that reflects different pipe materials. يعني حسب الماتيريال type بنحدد N. So C1 and N will be provided for you, will be given, and you can express then depending on the material you use اللي هو بيحدد لكم the values of C1 and N. This will give you the cost per unit length of the piping system. Okay. Now, other costs includes, we have the cost of fittings, valves, pumps, supports, etc. So to assess these costs, also we need information. كمان هون, okay, في عنا a tool that this cost is related to the cost of the piping system. يعني نحن شفنا انه C1 times D to the power n هو الpipe cost. We can define a factor which is a multiplier of the pipe cost system, and it has typical values between 6 and 7. يعني عادة إذا البايبing system, إذا الcost of piping, let's say $1,000 for example, بيطلع عنا fittings و valves و pump between $6,000 $7,000. So this is how the friction, this factor, multiplier factor, will also be provided for you. Okay, so now you can express both pipe cost will fittings, valves, pumps, and installation cost function of D. Okay, now what also we can have, therefore, once we determine the cost of the piping system and the cost of fittings, okay, we can find now that the total cost of the system is Cp plus Cf is 1 plus F times C1 times D to the power N. Okay, and I repeat, C1 and N are properties of the type of ducts you are using. F is a factor, a multiplying factor that will be between 6 and 7. Now, after when we calculate the total cost, now we should consider the amortization rate, okay, as well as the maintenance costs. لأنه نحن هون ما أخذنا into consideration the maintenance cost. A way of implementing the maintenance cost إنه من بعد ما نجيب التوتال cost بنقول إنه بدنا نزيد a certain fraction, okay, B, fraction that is related to maintenance, okay, and this fraction will be also provided for you حسب the problem, and it will take into account all annual maintenance cost required. Okay, so the total إذا بدكم cost لحديت هلا صار taking into consideration الامortization rate هيكون plus الفراكشن B اللي هي due to maintenance صار التوتال cost A plus B times 1 plus F times C1 D to the power F. Okay. Now, the contribution of the cost of moving the fluid through the pipe system يعني في بعد أخذنا maintenance cost بعد في operational cost. To consider the operational cost, okay, the operational cost can be calculated function of the cost of energy we are using in dollars per kilowatt hour. Now we should take into account what is the time of operation of the system, okay, so per year. يعني انتو when you multiply C2 اليونت تبعه dollars per kilowatt hour, when you multiply by hour per year, okay, عنا الhour والhour will simplify. So you have لأنه هون عنا hour بالdenominator هون بالnumerator. So now the unit will be in dollars per kilowatt per year. Okay. And then انتو هدفكم آخر شيء تجيبوا الcost in dollar per year. So what should you do? You should multiply by the number of kilowatt used. So the number of kilowatt is related to the power used. So dW by dt is the power that must be supplied to the fluid to overcome head changes and frictional effects. So when I multiply C2 by T by the power, I will get my total cost in dollar per year. Now, I should not forget to divide by the efficiency of the equipment لأنه على طول efficiency is less than 100%. يعني مفروض أنا أعطي power over to take into account losses that can take place. So I should divide this result by the pump efficiency to get the pumping operating cost. And now, okay, concerning the power dW by dt, this power can be expressed. How can I find it? I can find it function of the following parameters. I need to know what is the mass flow rate to be supplied, what is the friction factor in my system, what is the total pipe length, okay, and what is the value. So here, if you want, this relation is related to what? This is m dot times losses and the variation in energy of my system. The energy of your system is assessed by the following term. يعني انتوا بتعرفوا انه ال H هي head, okay? The head at any point the energy head can be divided into pressure head, kinetic head, and elevation head. So if you want to go from point 1 to point 2, if the energy level, if the total energy level at 2 is larger than 1, this requires additional power. So this is for variation in elevation head in energy. So to get to get the value of the power, you should multiply m dot. Yeah, guys, can you please mute your microphones, please? So you have m dot times delta H times G. This will give you the unit of power. Okay, so this is the power required to take into account changes in energy between the two locations, and this is to take into account for friction loss. Okay, so now we can compute the power required in kilowatt or in watt, and then I can now replace in the total cost relation. And until now the total cost includes هيدا الترم 1 times C1dN هو for the cost of piping material. Plus F is to consider the fitting parts والvalves والpumps. A هي for taking into account the amortization rate with time. And B is to take into account maintenance, here the fraction of maintenance cost, and this is the operational cost. So now we end up with the total cost expression. Okay, now in order to find the optimum economic diameter that will minimize the total cost, we need to differentiate the above equation with respect to the diameter. Okay, and we will set the result equal to 0. If we do this, okay, we'll not go over details of derivation. Okay, just you should understand the procedure here. It's a little bit complex. The final expression for the optimal diameter is this one. So in a problem, if I give you all of parameters, you can use this relation to find the optimal diameter. Okay, so I need to give you the friction factor, the mass flow rate, the value of coefficient C, the time of operation, the efficiency of my pump, the factor F, the multiplying factor F, the amortization rate, the fraction of maintenance cost, and all of these parameters that were already defined before. Okay, I will use them to get the value of the optimal diameter. So we can note that the optimum diameter is a function of the friction factor. In addition, it's a function of several variables as the mass flow rate, the efficiency of the pump, the maintenance fraction, etc. Now, because the optimal diameter is function of the friction factor, then we need to have tools to get F. Okay, so like these tools are similar to Moody diagram, but are different than Moody diagram, because in Moody diagram, as we have seen before, you need the Reynolds number and epsilon over d to get the diameter. Okay, and here you don't know the diameter before, so in order to get F, we need to come up with charts, okay, that will help us into finding, if you want, F and the optimum. And we can do this, we'll see in the following results how to do this, what are these charts and how to use them. Okay. Okay. So let us see how we build these charts. First, as usual, we need to define dimensionless numbers that can be used, okay, to draw our figures, our charts that can be after used in general cases. Okay. First, what is a good dimensionless number here to use? We don't use epsilon over d as I told you, or Reynolds, because they contain diameter, and diameter is unknown. So what a strategy is here to use the roughness number, as we did, if you remember, in the case where d is unknown. So we used a certain, we replaced the Reynolds number here by rho. We replaced, epsilon over d by rho, because this helped us into reducing the number of unknowns. So here also we'll use this concept. So we'll use the roughness number as one dimensionless parameter. And we will use a relation between the Reynolds number and friction factor. How to do this? So we already have developed here. Okay, here we developed a relation between the optimum and the friction factor. We can develop also a relation between Reynolds and the friction factor. And we can show that this relation is of the following form. So we can derive a relation between the friction factor and the Reynolds number that is related to all parameters involved and defined before, which are mass flow rate, efficiency, fraction of maintenance, costs, multiplying factors, C1, constant C1, C2, and etc. So you are not responsible of how we got this relation. What you should know that knowing these parameters will allow us to find a relation between the friction factor and the Reynolds number. Okay, so now from here the idea to draw a chart, to draw the following chart. This chart is formed by the following parameters. I have على x-axis I have the parameter f times Reynolds n to the power n plus 5 كلها سوا to the power 1 over 6, because I am able to assess this parameter function of the variables given. Okay, and also I can calculate the value of the roughness number since it's independent of the diameter. So this will help me from this chart to get the value of the friction factor. So as you can see, for different values of n, okay, we get different charts. So here, what is n? If you remember, if you go back to the equation here, this is n. N was this parameter here. Okay, it is a parameter related to the pipe material we are using, because when we define the cost of piping system, we said that n is a dimensionless exponent in pipe cost equation that will reflect different pipe materials. So we have different values of n, and these charts will be developed for different n. So for each n, we'll develop a chart. Okay, and we can see here that this chart can be given for us, so that for a certain knowing the value of n, I can go to the chart and I can compute the value of f Reynolds n plus 5 times 1 to the power 1 over 6, and I get the raw number for my problem, and this will allow me to read the value of the friction factor. Okay, we will do this in examples to see how to apply it. Now, graphs have been developed for different values of n, including 1, 1.2, and 1.4. So of course, if I will give you a problem, I will select n as one of these three. I will not give you n different than these, because in this case, you will not have the chart. Okay, and from the graphs, we can find Reynolds and then the optimum economic diameter. How? Because when you get f, once you know the value of f, then you can go back to this relation, because you know the value of f Reynolds n plus 5 times 1 to the power 6. So once you get f and you know the value of this number, you can deduce Reynolds. And knowing Reynolds, you can deduce the value of d. Okay, so the optimization technique was used to develop relations that are drawn in graphs. So in this way, I can select the optimal diameter without having to go back to equations. I can just use these charts to get the optimal diameter. Okay, so let us consider some examples. So before going to examples, we have seen that the preceding equation developed okay, are difficult to apply for non-circular cross-section. Therefore, an optimum economic diameter is first calculated for a straight constant diameter circular pipe. So here they are telling you what to do if we want to find what is, if you want if you want to design a system that does not have a circular cross section, and we want to find here, instead of talking about optimum economic diameter, okay, because in this case the cross section will not be circular, we'll talk about an optimum economic velocity. And what is the method used to get this optimum economic velocity? To be able to use the previously developed charts, what we will do, okay, we will first consider the area, okay, and we'll find the corresponding straight constant diameter circular pipe of equivalent, and you can find the equivalent, okay, the equivalent diameter for the section you have. For this equivalent diameter, okay, you can use the previous chart to calculate the optimum, okay, and you assume that I have a circular section. Despite that I don't have it circular, I have it of a certain shape. But as a first step, I consider it's of circular shape. I determine the optimum. Now, knowing the optimum, I find what is the cross-sectional area by doing pi d square over 4. Okay, and knowing the cross-sectional area, I can divide by the flow rate. Yani I have the flow rate given, Q is given. I divide by the corresponding cross-sectional area, the equivalent cross-sectional area, and I get what is called an equivalent velocity. Okay, so now instead of talking about an optimal diameter, I talk about an optimal velocity. Okay, and once I determine what is the optimal velocity, then I can deal with my with the cross section of my geometry. And I don't have to consider it as circular. I assess the real area of my. I work on the real area that I have. Okay, so when we have non-circular cross sections, the strategy will be to optimize the velocity, and we find the optimum economic velocity, and therefore this strategy will be used to size the dimensions of a non-circular duct, and then fittings can be added to the pipeline as appropriate. So I will select the corresponding dimensions of the geometry I have to give me this economic velocity, knowing the value of the flow rate. Okay. Let us consider the following example. We have oils to be pumped from a tank to a bottling machine. The machine can fill and cap 32-liter bottles in 1 minute. We want to determine the optimum pipe size for the installation using the following parameter. So look, they gave us all parameters needed. They gave us C2, C1, T, F, N, A, B, the efficiency, and the type of material used. It's PVC schedule 45. Okay, so what we can do here is first we can say that we want to find the optimal diameter. Okay, so to do this, we need to use the corresponding equation developed in the optimization process and the Moody diagram. Okay, so first, the first steps of the problem are very similar to what we did before. We should find properties from tables. So we have a certain type of oil. We go to table B1. We get rho and mu. Since it's PVC pipe, it's a smooth pipe. Epsilon is 0. So now we can find our parameters. First, we want to calculate the volumetric flow rate Q. Okay, the volumetric flow rate Q here is given because they said for us here that Q is equal to 30. So we have 32 liters per minute. Okay. And we can convert to meter cube per second by just saying that it's sorry, it's 32. It's not 32. It's 30 of times 2 liters. Yani I should fill 30 bottles, and each bottle is of volume 2 liters. So it's 30 times 2, not 32. Okay. So 30 times 2 will give me 60 liters per minute. And now I want to convert units to meter cube per second. So I just have to multiply by 10 minus 3 and to divide by 60 to get the value in meter cube per second. Okay. So this is for the flow rate. Knowing the flow rate, if you are you know that one of the parameters in the equation needed is the mass flow rate. Mass flow rate is simply rho, okay, times Q. So I should multiply Q by the density because the unit of Q is meter cube per second and the unit of rho is kilogram per meter cube. And this will give me the unit of mass flow rate, which is kilogram per second. So now I can compute the value of m dot, okay, from this information. Then now I can use the formula for the optimal diameter, okay? The optimal diameter is function first of m dot, which was calculated, C2 given, T is given, N, A, B, F, C1, the efficiency are given, and rho is the property we got from the table. We still have only one parameter to find, which is the friction factor. Because if we don't know the friction factor, we cannot get the optimum diameter, okay? So to get the friction factor, we need to use the diagrams we have, okay? Now, look, if you have a laminar flow, okay, you can use the formula for friction factor that you already know. And here, for example, okay, how to know if it's laminar or not? You should do, if you want, you should make an assumption because you cannot know before calculation if the flow is
دكتور
laminar. نعم.
بس بدي اسال سؤال. هلا نحن بهديك السيشن اللي شرحتي فيها اكسرسايز
نعم.
نحن ما عملنا بس عملنا وقت كان عندنا الكيو unknown بس كان كتير طويله كمان يعني ممكن كمان يجينا diameter unknown.
هذاك الاكسرسايز ما كان في F1 و F2 unknown. اوكي كان عندك two friction factors unknown and you should solve for them by trial and error. اوكي you assumed values of F1 and F2 وضلينا نعمل iteration بالمودي diagram لحديت ما وصلنا ل convergent case. يعني صار عندنا very close result.
في exercise عملناه كان Q unknown.
اما هيدا هو بعتقد لا مش تبع F1 F2 اللي عملناه مرة الماضي هو تبع F1 F2.
اوكي
عملنا
أوكي.
شيء
ممكن
ثاني
يجينا مثلا
ايه
ما
اكيد
نحن ما بعرف عملت كذا واحد مش متذكر.
ايه كل اللي عملنا بهنن معقول يجوا مثلهم.
ايه بس انه ممكن مثلا يجينا ما نحن او يعني وقت كان عندنا للتست كان عندنا كمان انه وقت يكون الاريا انه معقول يجينا هون كمان عم تطلع كثير كبيره صعبه.
اوكي لا انه I will give you problem ما تعطلوا همه ما اعطيك شيء كثير طويل بعطيك شيء بينحل اكيد.
سيميلر
نعم
يعني سيميلر لهدول اللي عم نحلهم
similar او اذا شيء different ما بيكون صعب يعني بيكون بينحل. اوكي مش ضروري يكون نفس الشيء بس في يكون نفس الكونسبت وما بده كثير وقت. اوكي طيب so now to get the friction factor to get the friction factor okay you know that for a smooth pipe in case the Reynolds number is small فيني اقول انه friction factor is 64 over Reynolds. هلا هون ما فيني بدي اعمل assumption انا ما فيني اعرف من قبل اذا الفلو turbulent او لا. So let us make the assumption. Okay if we consider, because it's a smooth pipe, I can make the assumption of laminar flow, okay? And I should verify at the end when I am done with the calculation, I should verify that my flow is really laminar. So if I assume my flow, يا شباب ما بقى حدا يعمل annotation. If I assume the flow to be laminar, then I can say that friction factor is 64 over Reynolds. And the Reynolds number is rho VD, can be defined function of the diameter. أنا بعرف إنه Reynolds number is rho is related to the viscous effects over, so mu over rho VD. مظبوط? If I replace mu rho V by their values, بيصير فيني أجيب Reynolds function of D. Okay, so if I substitute the Reynolds number by its expression function of D, then I get that the friction factor is 64 over Reynolds equal to 1.75 D. فصار معي في F function of D. So now I can substitute in the equation of the optimal diameter. لأنه my purpose is to get D. So if I replace here F by its function of D, بيطلع لي values of D optimal. Okay, so in case the flow is laminar, the solution will be straightforward. لأنه just I have for a smooth pipe إنه friction factor is 64 over Reynolds. So let us make sure من بعد ما جبت D optimum, I want to make sure إنه my assumption is true. So I should check for Reynolds number. For this value of D, if I plug in the Reynolds number, I get that Reynolds is 1,488, which is smaller than 2,100. So I can consider then that my assumption was right, and it's really a laminar flow. So now I am done, لأنه لقيت ال D optimum, ولقيت ال corresponding Reynolds, and I can calculate the corresponding friction factor as 64 over Reynolds. So in this problem ما عدت charts لأنه طلع الفلو laminar وطلع فيني استعمل الفريكشن فاكتور for a smooth pipe اللي بعرف إنه هي إذا كان laminar flow هي 64 over Reynolds. بما إنه I verified إنه الفلو is laminar, I can stop here. لو طلعت الassumption wrong, then I should use the diagrams. Okay, so I should repeat the procedure and use diagrams. Okay. We'll use examples on diagrams. We'll do examples on diagrams next time. Any question before we stop?
ميرسي دكتور.
Merci لكم. See you on Thursday, okay?
دكتور
نعم.
بس في نسألك كنا أنا وجوزيف يمكن عنا الاف واي بي 20 الاف واي بي معك كمان أسألك إذا نهار الخميس فينا نسمع بعد الصف ولا مش
فينا
قادر؟
نعمل الخميس yes بعد الصف.
ودكتور بس كمان السي اف بي مش الحال للأنسس.
انتم مش حالكم، انا بكره بدي اخذ كمبيوتر على الاي يو بي جرب ظبطه.
نحن حكيناهم بالجامعة بطل عم بيظبطون.
بطل عم ينزلوا انسس بالجامعة؟
لا ما
حجرب ان شاء الله
بدنا نجيبه.
طيب ان شاء الله يمشي حاله عندي ولا بصير بدنا ننزله من برا. اوكي.
طيب ودكتور انت بتعرف حدا من برا بينزله؟ مين
ما كان المفروض بينزله؟ منه هالقصة الصعبة يعني. إذا بتروح على حيلا محل كمبيوتر بينزلوا لك إياه.
بس مش إنه ينزلون على الكراك أحسن يصير فينا نفس الشيء.
لا بلا لايسنس، بيعطيك إياه بلا لايسنس، بصير يفتح أوتوماتيك.
أوكي.
يعني على السيدي بينزلوا سيديات بينزل لك إياه. حتى فيك تنزل student version free online إذا بدك. هلا بتكون شوي limited الكاباسيتي بس ما عليها بنشتغل عليها مش مشكلة. نزلها online إذا بدك. free you can download it for free online.
اوكي ودكتور بس كنا نسأل كرمال العلامات.
نعم.
نحن عنا شيء ريز بالصف ولا ما عنا؟
ريز؟ هلا لحديت هلا الافرج منيح، الافرج بال 75 بس انه كل
دكتور نحن نجح عنا 70 يعني الريز ابدا مش منيح، العلامات ابدا مش منيح.
ايه نحن عندنا 70 هي المعدل، بس انه
طيب
يعني اذا جايبه 75 ما بيخلوك تعلق اف واي بي،
طيب
بدك يكون 75 وما
ليكو ان
فوق.
شاء الله بتحسنوها، بس كنت تعملوا شوية effort، لانه هلا بس رد لكم الفحوصات هتشوفوا انه في كتير concept errors عاملينهم، لانه ما كنتوا فايتين مزبوط بالديتيلز. هول small details لازم تنتبهوا لهم for next time. وان شاء الله
هو دكتور
ان شاء الله
بصراحه
بيعلوا، يعني ان شاء
بس
الله
معودين
بيعلى
دكتور
الافرج. نعم
نحن دكتور، بس انا معودين بهالكورس انه من قبل من التلاميذ اللي ياخذوه انه ما كثير بيركزوا ديتيلز، لانه كان هو بس يقدموا بروجي وكلهم
طب يا
يقطعوا
شباب،
على الهينه،
هلا
يقطعوا
الكور
95
اوكي
98.
ان شاء الله
بس
خير.
راح شوي ظروفنا يا دكتور، معلش.
يا عمي رح راعي ظروفكم، وانتم كمان شدوا حالكم شوي كمان.
لك اكيد والله، ما نحن عم ندرس، طب كيف جبنا هالعلم اذا ما درسنا؟ بس
طيب
بيكون غلطنا اشياء ما انتبهنا لها.
اوكي مش مشكلة، البروجي كمان
لا
بيعلي لكم علامتكم، دونت وري. اوكي
مش مشغل، بنحكي بالصف. ميرسي كثير لك دكتور.
اوكي يلا see you next.
طيب ميرسي
باي
دكتور.
باي باي.
باي.
دكتور هلا الخميس شو راح يكون عندنا بس الهوم ورك؟
الهوم ورك ويمكن اذا خلصنا discussions بنكمل examples.
اوكي ديل.
اوكي يلا باي باي.